Chandrasekhar lectures.
And I promise you the last.
And you promise us the last. Okay. So Itamar, go ahead.
Right. Since we are in Chandrasekhar lectures, I got yesterday from Spenta, I think it's a wonderful picture that you took. Not only because it's very Chandra, you know, he always seemed to have been very modest. He wasn't. But he really was always sort of making the sort of show of being extremely modest. But still, he puts the picture of Isaac as low at least Sir Isaac, at least a head below. Did you insist on having a few books here to bring it up? I don't know. Huh? That's a Principia, I see.
Yes, it is. It is.
Anyway, he was a really wonderful person. I'm really happy that I had the chance to meet him, and I'm also very happy and very thankful for the opportunity to give some modest lectures in his memory. So today I'm going to change subject a little bit, and I'm going to discuss with you what happens when you take into account the fact that amorphous solids can have also other degrees of freedom. For example, we're talking about metallic glasses. We discussed yesterday metallic glasses. These are metals, and they're made of a few metals alloyed together: nickel, iron, cuprum, etc. And some of those have magnetic properties. So the amorphous metallic glasses can have magnetic properties, and then one finds extremely interesting new instabilities and catastrophes in magnetic amorphous solids. There are interactions. And this is a subject that has really been, for some reason, neglected, in the sense that in the past, there's been, as you know, enormous amount of work already on amorphous solids. There have been tremendous amount of work on crystalline magnetic materials with or without random interactions, but where the particles are stuck in crystalline order, and surprisingly little work on a very interesting subject that is amorphous solids with magnetic interactions. So this is what I would like to tell you today. You know, it's a huge subject. The parameter space increases dramatically. There are many new interesting effects. So there is a very special combination of magnetic, elastic, and magnetostrictive properties. What is magnetostriction? Magnetostriction is a well-known effect that is being used in every clothes outlet in Bangalore. So you don't steal a shirt. They put this thing that if you try to steal it, bzzz, goes when you go through the gate. This is magnetostriction. The materials change their volume when a magnetic field is put on them. So you have an oscillatory magnetic field in the gate, and the stuff that is attached to the shirt changes its volume under the oscillatory magnetic field. And the volume of the system. Fact that if you press the system, when you compress it, it creates a magnetic field, etc. We always have to remember that our research is curiosity driven, but it doesn't harm when there are also technological applications. In fact, to these metallic glasses with magnetic interactions or properties are beautiful technological applications in the field of sensors and surveillance. So, I mean, even though this should never be a reason to do our basic research, it helps. And let me make a short introduction to the mechanics of amorphous solids. It'll be really very quick, just to remind you of what we discussed sort of yesterday, and then I'm going to discuss what differences appear when I add magnetic degrees of freedom to the models that so many of us study. So we said yesterday that the carriers of plasticity in crystalline materials are dislocations. On the other hand, that they don't exist in glassy materials, which are amorphous. We discussed the fact that the response to an external strain is very different in the sense that it's affine to an affine transformation and it's non-affine to an affine transformation in the glass. We discussed what is plasticity. We looked at the affine and then the non-affine response. And from that, looking at the condition for equilibrium in a athermal quasi-static straining, we came up with the equation for the non-affine response in terms of the Herschel matrix and the so-called non-affine force. We discussed the fact that when there is one eigenvalue here that goes to 0, which is an instability, the non-affine field is dominated by the eigenfunction that is associated with this fellow. We said that there are instabilities with the eigenvalue of the Herschel matrix that goes to 0 like a square root. They are a saddle node bifurcation, which is very useful for discussing all kinds of properties. This exponent determines other properties and things. And we said that the eigenfunction localizes when the eigenvalue goes to 0. And we said, aha, this is also modelable. We can model this with Eshelby solutions. Okay, so this is when you don't have any magnetic things. So now I'm going to discuss two models of metallic glass and try to show you how many interesting new results can be there. So now the energy, which before was only a function of the position of the particles, will now also be dependent on a set of variables that let's call them spin variables. And a very simple model that you can build up is going to be made of a addition between new mechanical that can we take as any one of the models that have been discussed in a couple of days that we were here, Cobb-Anderson, any binary mixture, and other cases. So this is the usual glassy Hamiltonian that we all know and love. And then there is a magnetic part that depends on both of the positions and on the spins. And now it depends on you. You can choose. I decided to go in the footsteps of Harris, Plischke, and Zuckerman, who have introduced a very interesting Hamiltonian already in the late 70s, in which the spin variables, since we're going to do the work in 2D for a beginning, we're going to take the spin variables in XY model in the plane. And we're going to assign, if we have a binary mixture, we're going to assign spins to one of the types of the particles. So we're going to do sort of Cobb-Anderson type of stuff. And we are going to have two types of particles, A and B. And one of them will have spins, the other one will not have spins. And the magnetic type of interaction, I'm going to write it explicitly. So the magnetic Hamiltonian, in terms of the positions and the spins, is going to have an exchange interaction as usual. So in the plane, this is going to be a function of the cosine between the angle that SI has on the circle, on the XY circle. So cosine phi I minus phi j, which is simply just SI dot Sj, of course. So this is the usual exchange interaction. Here, the third term is simply the interaction with the external magnetic field B. Magnetic field B here, this is the Bohr magneton, and this tries to align the spins in the direction of the external magnetic field. We'll always take the external magnetic field to be in the X direction when you have an XY system in the plane. So this is going to be proportional to the cosine of phi I. Try to get it to 0. The more interesting term, which comes from this analysis of Harris, Plischke, and Zuckerman, has to do with local anisotropy. Let me explain local anisotropy. This comes only when you have magnetic things. You see, when you have a crystal, with magnetic properties, there's always a easy axis because of the symmetry. And the spins are preferring to be in the direction of the easy axis. Now we have a random system. But a random system doesn't mean that locally you don't have structures. Okay, so in fact, we are going to have locally a typical angle theta I that I'm going to define in a moment. And the spins are going to try to align with the local angle theta I, but theta is has an index I like the particle. So every particle is going to define a preferred local direction. This is known as local anisotropy. And the way that we choose this theta I is the following. You look at all the neighbors of ith particle, and you now look at the tensor of the interparticle distances Rij alpha, Rij beta. So this is the vector distance between particle I and j. That's the alpha component out of x and y. So Rij alpha, Rij beta. You weight with the interaction, which is the exchange one, which is of a finite length. This will make now a tensor T, Ti alpha beta. You now diagonalize this matrix and you find the two eigenvalues. So if the local arrangement around the particle is isotropic, then the two eigenvalues will be the same.
How do you define the neighbors?
Sorry?
How do you define the neighbors? It's not on the lattice, right?
No, but you have these distances, okay, Rij, the distance between particle I and j, and this is weighted by the exchange interaction that depends also on the distance Rij. So this Rij is going to look something like this. Okay, so those that are close by are going to contribute more. Those that are beyond the interaction are not going to contribute. So it's the local neighborhood that is going to. Well, you could get sharp. We actually don't do anything sharp because we want to compute Hessians. So it goes to 0 with two continuous derivatives. So, I mean, we don't like sharp things because then theory becomes unpleasant.
J always has the same sign. It doesn't oscillate.
No, it doesn't oscillate. It's a given function, so there's no randomness here. Okay, the only randomness is very different from spin glasses. There's no random interaction. The only randomness is because of the glassiness of the positions of the Ri. Okay, so J is a given function, and it becomes quasi-random because the Rij's are quasi-random.
It's not like RTKY zero. It's the metals. There could be RTKY interaction.
Say it again?
Since we are talking about the metallic class,
Yes.
there are electrons.
Yes.
There could be RTKY interaction.
You're absolutely right. There is an electron C there, and you may or may not want to take it into account. Of course, if you want to deal with conductivity, you have to. But at the moment, I'm sort of putting it aside. In fact, if you ask Ratul, he'll tell you that we try to do work comparing mechanical properties with and without the electron cloud, and they're not very different. But of course, for conductivity, it's going to be absolutely essential. Anyway, so I'm trying to say that we are now taking the eigenvalues of this tensor, kappa 1 and kappa 2. If they are the same, then the coupling constant k goes to 0, then it shouldn't matter.
I think the question was because of RKKY, could you have sign changes in the interaction?
In J. Is this what you ask? Also possible. Not in this model. Okay, thank you. I'm sorry that didn't, yeah. Okay, however, if the local region is n isotropic, then the eigenvalues kappa 1 and kappa 2 will differ, and then I will have some contribution here to Ki. To Ki. This is a very important term, it's a very interesting term in terms of the dynamics. And in fact, if you notice, it's the only term that really couples between the mechanics and the magnetism in the sense that it is really sensitive to the local arrangements, where the others, this is only a function of the Ri's, these are only functions of the phi, but this term here is the source of interest, the coupling. From this comes magnetostriction, from this comes all the interesting phenomena in this model. So is this clear? I mean, because this has to be clear, because I'm going to assume. Sorry?
Some coupling between the two because of the J. The mechanical part and the spin part are coupled of the truth.
You're right, but this is in fact a stronger sort of effect. But you're right, there is also a dependence on the distances between the particles here. Yeah.
Why cos square?
Because I don't want this to be dependent on the, see, I mean, anisotropy axis is not a vector. It should be independent whether it's this or or this, okay? So this is why it's cosine squared. It should be pushing the phi I in the direction of that I, both for such phi I and such phi I. Okay, so that's the sort of model. And then I'll show you the results of this model, quite interesting. And when we started to discuss in public the results of that model, we were criticized that we didn't put long-range interactions also. So a second model that I'm going to discuss later will introduce also long-range dipole-dipole interactions. So there will be a somewhat different model. It's going to be now with spins SI on a three-dimensional Heisenberg sphere, and going to be an exchange, going to be anisotropy in the z direction and in the plane, and also with a dipole-dipole interaction that is decaying slowly. And you'll see that this brings in interesting differences between short range and long range, and I'm going to discuss both models, so I'll go back to this later when I finish with the first model. So you can talk about many things. You can talk about magnetostriction, etc. I'm going to focus, because it's just one lecture, on one interesting phenomenon, which is known as the Barkhausen noise. Now, the Barkhausen noise was discovered experimentally already in 1919, and is a huge amount of work on Barkhausen noise, but not much theoretical work, as I say, on magnetic glasses. So it's usually manifested as a series of jumps in the magnetization of a ferromagnetic sample when subjected to varying external magnetic field. You actually hear this. You know, you ramp a magnetic field, you put a microphone, and you know, whenever there is a jump in the magnetic field, and it looks like this. So this is a typical so-called Barkhausen hysteresis curve. Here is, I'm sorry that I don't have the labels, this is here the magnetization. The magnetization in these units that we have here is nothing but the sum of the cosine of the phi I. Okay, so mu A times the cosine of phi I without the B. B, if you take here the B, this is the magnetization. So you can measure the magnetization, and you now plot the magnetization as a function of the external magnetic field. So you start from a fresh, as quenched system. Okay, you start from a liquid and you quench it. The first curve looks like this, and then when you come back, you don't go through the same thing, you come through here. And when you now change the magnetic field, you go through here, and from this point on, you're going to go through the hysteresis curve. You'll never see the fresh, as quenched behavior again. And what you see here is that there is a series of catastrophes or instabilities where there is a sharp change in the magnetization. You make a little change in the external magnetic field. So there is a large variety of such jumps, small ones, big ones, etc. They're steadily distributed, and steadily the statistics of such are very interesting. One of the reasons that we started to look at this is because there's been a lot of work, and recently some work that actually annoyed me, and I'm going to discuss this. So in the past, there was various approaches. People started to talk about the motion of magnetic domain walls across spinning centers, as mentioned yesterday by Monsieur van den Broek. People talked about self-organized criticality, simple old critical phenomena like Jim Setna, fractal domains like Gene Stanley, all kinds of approaches to explain what is going on. Some authors declare that the phenomenon is universal, and you always should get the same exponent in the description of the statistics of these singularities, of these jumps. Others declare non-universal. One of the things that got me a little bit upset was some claims of power law with exponent minus 1.5. Without putting names into the game, some people are running around showing 1.5 for any such sort of type of serrated noise, from earthquakes to Barkhausen noise through... Why do you laugh? Damien, don't laugh, please. It's not funny. This was not one of my jokes. This is the things that I suffer from, isn't it? And again, without putting names on the table, I think a lot of this analysis is simply, I would say, uncareful data analysis. I'm going to say from the start, evidently, this is a complex problem. In general, you should expect thermal effects, material dependence, ramping speed, type of randomness, etc. So as usual, what I'm going to do, I'm going to try to study this in the cleanest possible way, a thermal slow ramping of magnetic field, temperature 0, and try to see what we can say rather exactly or as precisely as possible.
No, just to be clear, you don't exclude the possibility that 3/2 exponent.
Sometime. But I think that the claims about the huge genericity of this are overstated, as I'm going to argue, as I'm going to show. It's a mean field exponent, yeah. But there has been claims about experimental examples where there's no reason in the world for mean field that somehow it works. So I will study this in this model. I'll start with the first model of metallic glass at temperature 0 in quasi-static conditions. Here, quasi-static condition would mean again that I'm changing a little bit the magnetic field, energy minimized, change a little bit magnetic field, minimize, etc. So what is Barkhauser noise? When you do think carefully, you actually can also understand what you're talking about. Well, at this time, you remember our beautiful matrix Hessian d squared u dri drj. Now we're going to have a larger matrix because we have a larger Hamiltonian. So it's again a symmetric matrix because its second derivative d squared u dri d phi j is symmetric with d squared u d phi I. This is a mistake here. One of these should be j, d phi j dri. It is symmetric, and you have now a larger matrix, and you can prove that the eigenvalue lambda of this H satisfies an equation of motion, such that when one of the lambdas, if it comes close to 0, will have an effective equation d lambda dp that is about a constant over lambda p. So this is lambda p squared going like db, d lambda p squared going like db. So again, square root singularity. It's a saddle node bifurcation. Here in this model is a measurement of log lambda p as a function of the magnetic field minus the point where one of these jumps occur, any of them, and you see that the eigenvalue indeed sits beautifully on a 1/2 singularity as expected from the theory. And what actually happens? When this happens, when you get a singularity, when you have an instability, at the same value of the magnetic field B, exactly the same value, you have a change in the magnetization that people want to call Barkhauser noise. At the same point, you have a change in the energy, and at the same point, you have a change in the stress. So this is a coupled system. You do the little change in the magnetic field, and a catastrophe happens, and catastrophes in all possible measured quantities, stress, energy, and magnetization. Again, I just wanted to make clear that magnetization is just the sum of cosine phi I. Here, it's normalized by the number of particles that have a spin. Okay, so now we can we understand what it is. We can do an arbitrary, accurate measurement of these jumps, and we can ask what is their statistics. So, of course, this is just a continuation of the last sentence. So, as I said, the same time that in the, so the eigenfunction now, the eigenfunction of this broader Hessian has a projection on the positions and projection on the span. And at the same time, this is not the same time, at the same magnetic field, this is an error, at the same magnetic field that the eigenvalue approaches 0, you have both a catastrophe or an instability in the position space and in the spin space. And what do you see here? You see a spin flip in some region. Okay, so everything is quiet, but a region spins flip, and this is the change of the magnetization. So that's what happens in the first model. Now, well, what we are told by some people who talk about universality, that you need to plot log-log plots. Now, when you try to plot log-log plots, there is an issue of how you choose the bin size. So here, these are the data that we collect for the probability to see a jump in magnetization of delta M as a function of delta M. And when you plot it with these beams, you have a very beautiful parallel over, I don't know, how many decades? One, almost two, with an exponent slope of about 1.6. Well, you change the beams a little bit. You make this now, these beams a bit smaller at this region here, and you get a slope of 1.46. Now, if I were a friend of some people, I could choose beams here to give 1.5 and publish it. Sorry?
If you have a power law field, so instead of plotting P of this thing, I will probably plot the cumulative distribution.
Sure.
That should be correct. No?
That's what I'm going to do. Yeah. I just want to use the opportunity to again warn people against log-log plots. You know, log-log plots are, I mean, they are dangerous, let's say it this way. They are, you know, you can get all kinds of things. I'm going to show you that the end result is going to be a slope of 1. So you see how hugely unreliable are log-log plots. So what you just said, one better way is to do the cumulative distribution, then you don't bin. This is continuous in Y. I even prefer the, how do you call this, the one that is unity minus Fy. It has even better properties, behavior. And this you can now do, and it looks like this. So when you do it, this is the data. Okay, now I'm taking the data and I'm trying to fit it. And I get the best fit in this red line here. You see, it's pretty good. There are a little bit of deviations here, maybe a little bit of deviations there. And if you believe this fit, you would say, aha, now we are getting a result that says that the best fit, by the way, with an assumption of exponential cutoff, the best fit is x to the minus 1.06, not quite x to the minus 1, but not 1.46, not 1.6, much lower, much smaller exponent. But when you fit this, you see, you have to assume something about what is the function that will give you the cumulative thing. So this is done under the assumption that there is a parallel multiplied by an exponential cutoff. Dangerous. As I'm going to show you, it's not an exponential cutoff. This is the integral, yeah, of course. This is taking data. It's also a good point that you asked. Let's say, let me go back here, which is also a dangerous thing to do, which we need to avoid eventually. I mean, probably you've noticed that here there are small jumps. Here there are small jumps. Here there are huge jumps. There's nobody that guarantees that the statistic is homogeneous over the whole cycle. It's not. Okay? So there's so many things to take care of, you know, that you cannot just blindly go and collect data and plot and claim log-log plots. Okay, so we have to be very careful. So let's be very careful. I mean, there's no escape. Huh? This is over the whole cycle. And you see here that, you know, this fit, which, you know, many would have said, wow, it's a beautiful fit. It's not such a beautiful fit. You know, one has to pay attention even to such little details, and they are indicative of something. So what is happening? What is happening? You see, this is a snapshot of the state of the system. This is now a color-coded snapshot where the color is the local direction of the spins. You see, there are regions where the spins are pointing in the same direction. So this is now angular color coding, and you see that there are regions of spins or patches of spins, and I'm going to argue that the Barkhouse noise comes because of flip of a particular such region or patch of spins. So let me introduce a probability that I'm going to call it P sub S, which is the probability to belong to domain of S spins. This is not the jump size. It's a probability to belong to a domain of S spins. Okay? Now, of course, the sum from the minimal size domain to the maximal size domain is unity. And I'm going to argue to you now, and this is very important, that there is a mean. You see, This is where the difference between mean field and non-mean field comes in. In a mean field theory, you always expect that when you go to infinite system size, your the spin patches are going to grow in size, and there's going to be no mean. Okay, it's going to grow. I'm going to argue that in such a model, the parameters determine what is the distribution of block sizes or patch sizes, and there is a mean. And this is fundamental to difference between a situation that will give you 1.5, maybe, you ask me, and a situation where it won't. Whenever you have a reason to believe there is a finiteness, that there's no infinite size in the infinite system size limit, then you have to do a different kind of thinking. And what I'm going to therefore do, I'm going to assert, okay, if I have a mean, my best guess on the distribution is to do the maximization of the entropy of PS, subject to the constraint that I have a fixed mean. And that, of course, gives me a distribution P of S that is exponential, goes like exponent of minus S mean over the average, and the average here is crucial, which is normalized by the average. This is normalized to 1 in the sum sense. Now let me introduce a slightly different quantity that I'm going to call f of S, which I need, which is the number of spins of size S normalized by all the numbers. And of course, the relationship is trivial between PS, which is the probability to be in one of them, and the number of them is simply S times N of S, the number of spins over N. And therefore, by changing variables, and I'm going to introduce a variable X, which is normalized to the number of particles that have a spin, you can easily get from this, by change of variables, a prediction for f of x, which is the ratio, which is the normalized number of patches that have x spins, where x is the normalized s. And the change of variables introduces x to minus 1 and the exponential here, and this is the normalization function, which is just the integral of this stuff here. I call it E1. Now you see that we already have an interesting exponent here, x to minus 1 times a cutoff function, but this is not the distribution of magnetizations, right? This is the distribution of how many patches I have of x spins. Now you see there is a subtle issue that if such a spin flips, the magnetization depends on where it was and where it goes to. Okay? So I have to take now into account, in order to get the magnetization distribution, the distribution of the angles of the spins. So I'm going to argue to you that in fact there are two types, there are more than two types, but at least two types of flips. Imagine that the magnetic field is pointing in the direction blue, and that I have a patch with a direction red. Now you see, if I flip here, I don't go through a maximum, you know, the maximum energy is orthogonal to the direction of that spin. So this is an easy one. It's an easy one. It doesn't require a large B, and this is going to be the type of things that are going on here, maybe the type of things that are going on here, but there's also another one. And the other one that I go all the way, let's say from here to here, this will take me through crossing the maximum of the energy here, and therefore you need a hefty B to do this. This is going to be this. This is going to be large, because the change in magnetization is the largest, is pi, okay? And these are going to be this thing. So, and in fact, I can do, I'm going to skip it now, but one can do in-Riemann type argument to identify the values of this B, and we can actually predict which will allow these and which will allow this to within a scaling argument, you know, up to numbers of the order of unity. But I'm not going to do this. I'm going now to discuss with you, for example, one of those. Let's say this one. And the other one can be done with the same way, so the same discussion. So let's do the PDF for the large flips. So when I have a large flip, I go from angle psi to angle 0, because I go all the way to being in the direction of the magnetic field. If x is the number of spins normalized, then delta m is x times this change. Okay? Now I'm going to argue to you that the distribution to see any psi is essentially random. Because of the randomness of the glassy material, the organization is sort of random, and therefore I can have any psi in the circle 0 to 2 pi. And therefore, now I'm going to compute the probability to see delta m conditional that I know the x. Okay? So what is this? I have now integrate over all the circle between minus pi and pi, d psi over 2 pi, which is this probability, 1 over 2 pi, and I just write this equation. Delta function of delta m minus x times 1 over minus cosine phi. This is what I need to compute. Okay, this is the delta m. This is just what is this argument says for the large flips, and then I need to integrate it over all the possible angles. Now I'm going to do the usual change of variables. So I'm going to say identity delta a minus x times 1 minus cosine phi is delta psi minus psi naught over x sine psi 0, conditional that the cosine psi 0 indeed satisfies the delta function. So psi 0 is determined by cosine psi 0 is 1 minus delta m over x. So I satisfy now the delta function. Now, of course, cosine phi 0 can be larger than 1. And this means that x must be larger or equal to delta m over 2, because otherwise I'll get, it can be either minus 1 or 1, but not larger in magnitude than unity, and therefore x is bounded from below by delta m over 2. So now I am going to rewrite the integral, so the same integral here, but I'm going to use this and put in what I know. So now I'm going now to integrate over x, because I have now the x here, and I'm going to see that everything that I need to know about p delta m is the integral from delta m over 2 here to unity, can be larger than 1 of dx. And now I put in what I've learned before about the probability to see x, which is f of x, and I have this term here, x sine psi 0, and I've already used the delta function. This is computable. I know the f of x analytically. So I can now compute the p of delta m, and it looks the following. It looks p of delta m is exactly 1 over delta m to the minus 1, times some cutoff function that is computable from this. A little bit ugly. Let me tell you what, when everything is said and done, what it looks. It looks like an ERF, an error function. It's an error function of this ugly variable. This is the cutoff function. The exponent is exactly minus 1, but the cutoff function is different. So now we can go back and understand what happened. You see, I was trying to fit an exponential function. Now the cutoff function doesn't quite agree. It's a bit smaller here and a bit larger here. For the large flips, I can do the same calculation for the other one. It's this one. So it doesn't quite agree. And this disagreement is the reason for what we said before, that we misfit a little bit here and we misfit a little bit there, and that's why we got, instead of 1, we got 1.06. This is just an example. You cannot get the right result without doing theory, because how would I guess that the cutoff function is ERF? Nowhere in the entire world I can do this. So we have here an example that we know now what is the answer. The answer has nothing to do with mean field. Exponent is minus 1. There's no reason for mean field, and I told you why there's no reason, because I don't have a mean field picture where the mean size of these patches is going to go to infinity in the infinite system size limit.
The assumption of psi is going to put 5.
Huh?
The probability of psi is going to put 5. The top one.
This one. This is crucial.
But that also means that the magnetization is 0.
No. Interesting. Okay, it's a good point. When I start with b equals 0, it's indeed 0. Okay, so the magnetization is 0. Now I begin to increase things. Now it begins to flip. Magnetization is increasing. The ones that I'm going to flip next are those that still didn't flip. So they come from the same distribution. Okay? It's a bit subtle, but it's okay. Because it's a continuous step. It's a continuous stuff. So this is why I can do this. Otherwise, it would be difficult to do. Now let me go and tell you about the second model because it's interesting. Second model, actually, the second model we did because of Franco Zapperi, who came to visit us at the White House and said, no. This is not what we mean by Barkhausen noise. Barkhausen noise we mean when there are patches, longitudinal patches of magnetization, when you have sort of long-range order, and when the Barkhausen noise is occurring because of the movement of the boundaries of these patches, and not because of flips. So we said, okay, let's take the long-range interactions that I showed you before. Let me go back to this. I wanted to tell you that we took the, how do you call it, the dipole-dipole interaction, just to make clear. So the difference, So the big difference is here that I take now the dipole-dipole interaction mi.rij, which by the way is another interaction term between the magnetization and the position. It makes everything different. There's a huge parameter space in terms of the parameters that you take here, k perpendicular, k parallel, etc. But nevertheless, let's just go and look at what we get, because I think it's still interesting. So what happens is this. Now you get a very different picture in which, indeed, as a function of the magnetic field, what happens is this. So here it is when magnetic field is 0, and you have 50-50 with the parameters chosen. This is Heisenberg, but we are choosing the parallel k to be 5 and the other one to be a quarter. So this makes all the spin pointing either up or down in the out of plane. So the green are, I can't remember which one. One color is pointing down and the other color is pointing up. So let me remind you, it's a two-dimensional strip, and now it's an Heisenberg spin, but we choose the parameters that goes either this way or that way. And now we're beginning to change the magnetic field. And as you see, what happens is that the patches are indeed increasing. So in this case, the magenta patches are moving on the expense of the green ones. The black ones, by the way, are those that have no spins. Okay, we have only one type of the particles with spins. And this should be, or maybe in the universality class of those models where you have a boundary moving, so to speak, or at least we should attempt to see what is going on. So here is the Barkhausen loop that you find, changing the magnetic field slowly. Looks like any other Barkhausen noise. And again, log plot. Now we said, wow, we get now again 1, because we have again the same exponent as we had before. Very beautiful, very beautiful. Wrong. You cannot do this. Again, I mean, even when you get a result that makes you happy, don't trust the log plots. Try to understand what is going on. And understanding again, I really want to pinpoint this point because it's really very crucial, also in experiments and in numerical simulations. Always look at the system size dependence. Always look at the system. It really reveals a lot. And we looked at what is the typical avalanche size. Okay, now by the way, the P of S that I'm going to now do is going to be of a different meaning from before. But now delta S is how many spins added to the magenta in one step. And you see that as a function of system size, I think this is an overshoot here, it sort of saturates. So as a function of system size, it's not going to go to infinity, it's not going to grow. And therefore we again not in mean field, and we need to begin to think how to deal with this stuff. So now we don't have flips, so we have avalanches. So the best way that I can think about this is the following. Let's now introduce a probability to see an avalanche of size S, from S min to S max. Again, normalized to 1, and making the point that I have an average. Again, you have an average, you have a probability. My best guess is to maximize the entropy, and then I get a probability distribution, which in this case is just an exponential. I don't now need to go to flips and angles and all this, because this is now a different kind of thing. I don't have angular dependence, it's either down or up. So I have a prediction. Well, here it is. So these are now different system sizes, 600 particles, 1,000 particles, 2,100 particles. These are the data. The red lines are the maximum entropy prediction without any parameter. There's no parameter fit here. And it seems to me that this, without any parameter fit, it's quite astonishing how good this agree with the data. So, you know, there's nothing more to say here. There's no scaling law at all. It's simply pure exponential, even though, you know, one can publish probably in Nature this thing here. You know, in all these tabloids, the Nature, Science. I mean, you know, by the way, that somebody recently wanted to start a new journal with the name Science and Nature, so that people will be able to say, I publish in Science and Nature. So, you know. But they didn't succeed. They got a low. They got a.
They didn't ask you to be the editor.
Anyway, so just to conclude, Barkhausen noise. I only talked about Barkhausen noise. There are other effects here. You know, as I say, magnetostriction, other things. We understand that at least in these models that you do glassy plus magnetic interactions, the Barkhausen noise is due to instabilities that are associated with plastic events. There's nothing else in this subject. Okay, these are the instabilities. So the delta M, if you want to understand it, you have to understand what happens with the Hessian matrix, eigenfunctions, eigenvalues, and you understand what is happening. The statistics is not homogeneous along the hysteresis curve, and you have to carefully understand what is going on when it's not homogeneous. The statistics are in general not power law times an exponential, sometimes not a power law at all, but even when a power law, not necessarily times an exponential. And what is this function sensitively determines what the exponent is. And I think that I have to end up with a somewhat pessimistic statement that without theory one cannot guess the right statistics. It's too delicate, and one really has to think carefully about what is the physics behind the phenomenon in order to say, aha, the statistics is this. This is a warning to experimentalists. Talk to us theorists. I mean, don't publish log-log plots without talking to a theorist. Thank you very much for your attention.
These are fixed particles.
No. They're glass. They're glass. They are moving. You change the magnetic field, they move. They have a non-affine response. They're not stuck.
So even during the...
Of course.
Okay.
Of course.
And
of course.
So dynamics, what is the dynamics you put?
But it's AQS. It's athermal quasi-static. So what I showed you now, as I said, I mean, I want to make a very careful experiment in the sense that I don't want ramping speed,
Okay.
and I don't want temperature effect. So it's a temperature zero,
Yeah.
and after every small step of magnetization, I energy minimize. So it's all the time in mechanical equilibrium, meaning that the particles will move around to annul the forces that are formed by the increase in magnetic field.
Okay. Yeah. So if,
sorry.
So if I consider this model on a lattice and dilute it, and just do the energy minimization on the lattice sides, do you?
It's going to be different.
So it should be similar result.
No, I don't think so. If it's on the lattice and the particles are not allowed to move.
No, they're allowed.
They're allowed to move,
but only to the nearest neighbor and with the minimization move.
I don't know.
I just dilute some.
I don't know.
This side.
I don't know.
Okay.
I don't know. I don't want to make a statement without thinking about it. Here it's a glass, and it continues to be a glass, and I'm free to move as they should.
I can probably still have a glass on a lattice, I guess.
If you call this a glass, call me Muhammad. I mean, what do you mean?
No, I mean in the sense that if I just coarse grain it and just each lattice point either can have one particle.
It's a disordered crystal. It's not a glass.
You do have plastic crystals.
No, what I'm saying is that I mean you have a
A glassy crystal is not a glass. It's a glassy crystal. Anyway, I don't know. I didn't think about it.
Sanjeev is saying that you can have this lattice gas model.
Yes?
Who has glassy dynamics, but
Yeah.
there are rules to determine
Yeah.
dynamics. There, if you put
Do it. Put in spins and see what happens. I have no idea.
Yeah.
Really don't know.
So, but what happens to the picture that we heard about yesterday, as far as this mechanical deformation is concerned? This magnetic degrees of freedom, that changes the picture, or it doesn't change?
As I showed you, now everything is coupled. So when you are going to put a strain, you're going to get magnetization
Yes.
and instabilities, and the instabilities are now joint.
Yes.
They occur to all degrees of freedom
Right.
simultaneously. So the eigenfunction of the Hessian is still the right quantity to consider,
Yes.
but has projection on the position space and projection on the spin space.
But do you get this Eshelby type of things when you project it to the position space?
Yes.
That's what I wanted to
You get Eshelby's. Not the same beautiful Eshelby's, but still sort of quadrupolar. And by the way, why is an interesting question, because you need to now do a new theory, which is not trivial elasticity,
Yeah.
but has to take into account these magnetic interactions.
So often when people do these log plots, Barkhausen noise is taken in the same breath as earthquake data. So do you think even in the earthquake data there might be something like this?
I think that everybody now should try the maximum entropy prediction on their data and see, you know, if it fits without any parameter, go home. That's it. I mean, it's really frighteningly similar to some of the stuff that people have published with fitting Paolo. Whatever you get, I mean, I'm sort of very doubtful.
So is there some model where actually one knows there is a power law?
Say it again?
Is there, so what is the model where you know for definite that there is a power
No,
law?
I don't know for definite, but I'm saying a condition for mean field is that it will be mean field, in the sense that if you have a distribution of things that happen, then the mean of the avalanches or the flips or whatever should increase indefinitely with the system size. Otherwise, you cannot be a mean field description. So if you can show that as a function of the system size, you have a mean, finish. No, you don't need to worry about mean field. Then you need to see what happens, but it's not going to be mean field. It determines if the mean avalanche is determined by the parameters of the system. Okay, and you can estimate it from the parameters of the system, and you can here, using Imrima arguments, then it cannot be mean field. It's not system size dependent. It goes to a finite limit when the system is increasing in size. So that's a necessary condition. It's not sufficient. You know, you may have critical problems that have correlation length going to infinity that are not mean field. But at least it has to go to infinity, otherwise it cannot be even mean field.
Even without mean field, you can still only have power, not in this model, but some other model.
We had power law here. We had a power law. We had a -1 in that model times ERFC or whatever. So I'm not saying the power laws are not possible. I'm saying that the predictions of mean field theory in these cases of Schroeder noise is a slope of 1.5. Now 1.5 can be from a mean field reason or from a non-mean field reason. All that I'm saying that you can abolish the mean field simply by looking whether you have a critical behavior in the sense that your average event increases without limit when the system is increasing, right? I mean, the fact that correlation length goes to infinity is easier in mean field than not in mean field, right? It goes with a different exponent than a non-mean field, but it still goes to infinity, and that's crucial. If you don't have it, then it cannot be mean field.
Yeah, sometimes people say that if you have the long range interactions, then the upper critical dimension is quite low, and that is why you get mean field exponents.
That's true, and that was the argument of Zaperi, who knows the subject very well. And he said, why did you try to put in mean field? Now you see, I have a suspicion that we need to go further here, that the story is not finished, because when you take the dipole-dipole interaction, it's a very weak interaction. It's long range, but it's very weak. If you integrate it in 3 dimensions, it is divergent. If you integrate it in 2 dimensions, it's not divergent. I suspect that since we have added the dipole-dipole interaction to a two-dimensional model here, and it doesn't make a big deal. It doesn't make it really long range. Next step will be to do it in 3 dimensions, where, now when I say 3 dimensions, I mean 3-dimensional film, right? A film, which is not a 2-dimensional layer, is still thin. But what the dipole-dipole interaction is going to do is going to try to minimize the energy by organizing the, the spins in opposing sort of linear regimes, right, to minimize the energy outside the film. But that's crucial when you do it in 3D, even thin film, but 3D because you have real divergent contribution. 2 dimensions, maybe it was not enough. How to do a mean field in 2 dimensions, I still don't know. Maybe we'll need to do 3D. So actually going up in the dimension.
I was about to ask the same question.
Yeah.
So this is in 2D and then you are claiming things. So I think
I'm not claiming, I'm just showing.
But,
there's a difference between claiming and showing.
Okay. But yeah, so at least a higher dimensions one should look at. And also this long range is a evolved sum taken care of. So you have to do evolved sum, right? If it is a long range interactions.
Yeah, but as I say, in 2D it is not divergent. The dipole-dipole, when we integrate it over the plane. But it does when you integrate it in 3 dimensions. So, anyway, I agree, we need to look at 3D.
So, Itamar, in the original Barkhausen problem, in terms of microscopic interactions, you don't need disorder. The disorder comes...
It occurs also in magnetic crystals.
Yeah.
It
Okay.
occurs
No, but
also
I'm
in
saying
magnetic
just if you just stick to ferromagnets, so the disorder there is arising in terms of the domain structure, right? So, but here you have a system where there is structural disorder, even if the magnetic interactions are not, they're not competing and there's no frustration.
Yes.
So what's the role of disorder in these systems as you understand it? Either structural or magnetic?
Well, I mean, I like the fact that you have a joint instability both in the positional and in the magnetic thing, and that you can still do it with a simple Hessian type theory. I don't know to say that this is fundamentally different or similar to Barkhausen noise in other systems that are ordered. I just say in this particular cases I understand what I see. And I believe that I can get a fairly good analytic description of the PDF. That's all. I don't know how to do it in other systems. I didn't try. And there's a lot of work also. I don't want to compete. People who did for years these first order, this critical phenomena kind of argumentation like Jim Setna and company, which is good work. I mean, also the work of Zaperi and Durin, who look at the dynamics of the borders of this, is very nice theoretical work. Whether it fits other cases of Barkhausen noise, probably not, as you see. So I'm saying the phenomenon is richer than what people try to claim. And the universality claims are a little bit overstated. That's all that I'm saying. And one has to look problem by problem. You remember, I started my lectures by saying that in nonlinear physics, unfortunately, we need to look at every problem individually. I mean, you have to understand what you see, what's the physics, right? You cannot easily, people try to jump and say universality class, it's all the same, but it's not.
Yes, Abhishek.
So at finite temperatures, I guess it's kind of more misread. So the jumps smoothen out, or what happens? Do you still get? What?
When you have a finite temperature, the picture will look much more dirty because you can go over barriers without the instability. You can say things, as I yesterday said something about temperature yield by computing the energy barrier for the t equals 0 problem, and then using this to predict something for t. You can do similar things here, but for example, when you start to deal with the ramping speed of the magnetic field, for me, hell breaks loose. I don't know what to say precisely. You know, you can do phenomenology and stuff, but really solve a model in a way that I can trust is more difficult.
Okay, if there are no further questions, let's thank Professor
Thank you.
Procaccia for a wonderful set of
Thank you very much. Thank you.
Pleasure.
Yes.